This is pretty much toward the end of this chapter. We here talk about the very general case of eccentric, actually combined eccentric and symmetric loading. So here there's so many cases. So, but here for illustrations, I simply pick this as one example. So if we consider a beam with the trapezoidal cross-section, and here if we consider the offline, which means the eccentric loading P applied here, and this P basically is away from the centroid of this cross-section, that is offset in both z direction and y directions. Okay, so this offset here, let me highlight, that is the offset distance, and that's the offset distance. This offset distance is B, and this offset is by A. Okay, so here to deal with these questions, the very first step is you have to how to say, redescribe the problem statement into the template or standard form that we've been used from chapter 2 about the axial loading. And in chapter 2, axial loading basically is here we have the loading P applied in the axial directions, and there we didn't emphasize, but in our template we assume the P is through the centroid. Okay, the centroid, basically the P is only pure axial loading. They wouldn't induce any bending. Okay, and also the template in chapter 4 we learned here in this chapter is about the pure bending. About the pure bending, here we consider is the beam that is symmetric in the cross sections, and then over that beam we apply the symmetric loading is such that the loading is applied to a plane of the symmetry. Okay, so here I plot the plane of the symmetry. In the plane of the symmetry, basically the plane passing through the centroid. Okay, the centroid of the cross section, and over the plane we have the bending applied. So for these problems here you have to translate or redescribe the problem statement into what we have based upon the standard template here. So here we see what we can do. So the first one we translate have the P to pass through the centroid here. So that is this one. So in this case, that fit into our case we learned in chapter 2. And in addition, because you have moved the P to the centroid here, so basically that movement will induce additional moment. For example, this P multiplied with A, that's going to cause equivalent the bending. So that is the bending about y-axis. Okay, and this one will be equal to P times A. And also the P, due to the translations and by distance, the B here, so basically here P multiplied B here, that you're going to induce another bending moment about z-axis, and let me call it mz, that is P times B. Okay, so basically this is PB and this is PA. So once you have this, then you can using the the decompose and apply the superposition principle. So for this case, okay, we say this is a cross section here. I simply look at from this viewpoint. Okay, the little guy sitting in this axis, looking from this viewpoint, and here we have three cases. So the first case is due to the axial loading that is passing through the centroid of the cross section. The second one is the bending about the y-axis. Okay, so this is the y-axis and my, okay, equal to PA. The third one is here. The third one is hard to displace in these two dimensions, so let me put into three-dimensional drawing here. Okay. So in the third directions, this is the z directions, and the third case will be the bending about the z-axis, so that is mz here. Okay, so if you like to use the double arrow sign, the symbols, basically the my is these directions, okay, the mz is these directions. Okay, so once you have this, then you can simply calculate is the stress. So basically the stress for this province, okay, then basically will be superposition of the three things. For this case is P over A, and for this case again, that one the stress is say we have this formula. For this case is the magnitude is my over I for this template. Okay, so we can try to apply it, and then from here let me say see if I have this one. Yes, okay, I have this one drawing, but anyhow, let me put into three-dimensional here. Okay, so I'm going to try and to better express my result here. Okay, so this is the axis, and so let me redraw this one. How about that? And to make that better. So this is the beam, the cross section, and I put into the three-dimensional. So this is our y-axis and z-axis, and basically the yz put into 4 quadrant here. So here we have the bending. Okay, so that is the my. So my applied to here, so that is, this is the axis, the neutral axis for this sub case. Okay, so for this case you can see this portion on the left hand side, that should be in tension, and everything on the right hand side should be in compression. And the same thing we look at here. For this case, the lower portions will be in tensions and the upper portion will be in compression here. So now for this case, then we simply determine the attribute. Then here we simply say the magnitude. Okay, so the magnitude in the put into this template is my over I, and we do this one by one. M is a moment applied. So for this case, M is my. Okay, and this one, why we know that is the distance between the point to the neutral axis. So for example, if we're interested, say this point here, so the distance between this point to the neutral axis actually is given by is coordinates. Okay, the coordinate in z. So basically the distance from here to here, that is his coordinates z here. So basically here is z. Okay, so let me say this point have the coordinate yz here. And I is a moment of inertia with respect to the neutral axis. Neutral axis here is y-axis. Okay, so this is the magnitude. And then, for example, if you're interested in this point, then this is the tensile. So you put the tensile here. On the other side, if you say you're interested in at this point here, okay, at this point again, say let me it has the coordinate yz, and of course for this case z will be you know that z will be negative, but anyhow that is the coordinate here. So again, the distance from here to here, that is the absolute value of the coordinate here. So we'll put the absolute value here. Okay, and now the point here is in the compressive region. So for this point here, you need to put the minus sign here associated with this point. Again, I use a color to indicate which point I'm pointing to. I just make 2 examples here. Okay, then for this one, then we can see, then for this one again, the magnitude is the template my over I. Okay, then we do this one. M is a moment we apply, that is mz. And again, we pick up this point which has the coordinate yz here. So again, this second one measure is the distance between the point to the neutral axis. So basically that is a distance here. That distance actually given is the y coordinate after absolute value here. So here, although you know the y is intrinsically is negative, but after the absolute value, basically that measure is a distance here. Okay, now I is a moment of inertia. So this is the neutral axis about the neutral axis, which is the axis. Okay, so again we exercise for this point. If we're interested, This point is with the tensor. So here with the magnitude, then you put a sign to indicate that's the tensor stress. And again, if you say want to calculate this point, okay, so the same as we exercise here, so that is a yz. So for this case, z has the negative coordinate, whatever. So this point again locating in the tension, so that is exercise you put into the positive sign with whatever the magnitude here. And again, if you want to exercise any point on the above, then you put in the negative sign. Okay, so from here you superpose individually, you should be able to calculate the stress at any point there. Okay.